Okay, so there's a lot of little details in this problem, and you just have to make sure to draw the picture carefully, and there's some geometry and some trigonometry that you got to do, but ultimately this is going to relate to a dot product. Okay, so let's follow the instructions. They give us a longitude and latitude for New York and for Moscow. Okay, so part one, Earth is a perfect sphere of radius, whatever. Great. I'm going to call that number R just because I don't want to have to write down the number all the time. So here's our sphere, like that. And let's see here. So North Pole on the positive part of the z-axis. Okay, great. So there's the North Pole. And the prime meridian is the x-axis, like so. Okay, so x-axis like that. So the y-axis is over here. Okay, so now New York, you'll notice, is 74 west longitude, which means New York is actually kind of over here like this, and then up a certain amount. So there's New York. Is that cool?
Oh, in the X, yes.
Yeah, I'm going to do N for New York.
Oh.
Yeah, because it's in the west direction.
West from the prime.
From the prime meridian. Yeah, exactly. Okay, so we know certain angles here. Specifically, for one thing, I know what this angle is. That is the latitude. So that's 40 degrees. And I also know this angle here. That's the west longitude, and that's 74 degrees.
Okay.
Okay. So let's compute the coordinates at this point, and then Moscow is very similar. And I'll let you do the Moscow one by yourself.
Okay.
Okay. Well, oh gosh. So let me drop a perpendicular here. And let's first try to find the coordinates of that point. Well, that point, I know what angle it's coming away from the origin at, and I can compute this distance. This is that's not the same as the radius of the Earth, right? Because the radius of the Earth goes all the way out to here. Yeah. So this point here is actually kind of, deeply embedded inside the Earth. Okay. So conveniently, though, that 40 there, I know that that's the radius of the Earth, r, and so this distance, little r, I'm going to call it, is just big R times cosine of 40. Is that cool? Okay. All right, now I want to know the x and y coordinates. Oh, I didn't. My y-axis didn't continue all the way over. That's not good. Let's see. Let's do this. So my y-coordinate is going to be over there. So I claim that x, you can just see from this picture, that x that I'm looking for, well, it relates to that angle of 74 by, well, it's r times the cosine of that angle. Yeah. So little r times cosine of 74. So that's something you can compute because you know r. That means you know this little r, which means you can compute this and now get x. Make sense? Y, similarly, is going to be little r. Now, it's tempting to say it's little r sine of 74. This isn't quite right. The problem is that I can see from the picture, because we're going in the west direction, my y-coordinate's actually going to be negative. So it's negative. Let me make this a little bit clearer. It's negative r sine 74 because it's west longitude.
Okay.
Make sense? Yes. Okay. All right, and then what's z? Well, z is actually one of the easier things. We don't have to deal with this little additional factor here. Z is just, I've got r. I know that 40 degrees. So this z is the same as that height there. And that height is just going to be big R times the sine of 40. there you go. All right.
Sure.
Okay. So, yeah, sure. Go ahead. So, yeah. So while you're doing that, let me just make a quick discussion here. That, by the way, if you want, you can have this piece of paper when I'm done, so you don't have to recopy. It'll save you some recopy time. Yeah. So Moscow is a similar deal. It's just that it's east longitude, so it's up at it's like maybe over in this direction and then up by some angle. So there's Moscow. And you can play the same sort of game. The main difference, aside from the angles being different, is that since this is east longitude, you're not going to have this minus sign here when you're computing its y coordinate. Yeah. Okay. So we know what n is, and we know what m is by this sort of calculation. Now, what do you do with this? Well, let's go to part 2 of the problem. Let's see here. Whoa. Yeah. So it says, what's the angle between these position vectors? So I want to know now. So I've got a position vector for Moscow, and I've got a position vector for New York, and I want to look at this sort of the great circle between those and ask what's that angle. Whoops, I'm sorry, I got tilted. Does that make sense? In other words, I want to know what's the angle between these two vectors, and well, that's the angle is related by n dot m equals length of n times length of m times the cosine of the angle I'm looking for. That is the radius of the Earth, right? The 3980 or whatever the number was.
Oh.
Right? Because it's the length of the this n vector, remember, is the position vector for New York, which is a vector that starts at the center of the Earth and goes to New York, which is on the surface of the Earth, namely it's a radius of the Earth. Yeah. Likewise, Moscow, also on the surface of the Earth. So there we go. And this dot product is easy to compute because I know the x and y and z coordinates of both of these vectors from the previous part. So you compute that dot product. You know that radius, solve for theta. Yeah, exactly. And the last part here, let's see here. Oh gosh, excuse me. There we go. So this last part, this is just goes back to a little bit of high school geometry. So in particular, if we're let's suppose we're going to fly an airplane from New York to Moscow, and of course they go in the shortest path, modulo weather issues and safety issues and stuff like that. But other issues aside, they take the shortest path. And I claim that's an arc of a great circle. And we know what the angle is, and we know what the radius is. And there's an old formula from way back when that the length of an arc of a circle is just the radius times the angle. So we just computed this angle here, theta. And so you plug that in here, we know the radius, and that allows you to compute the distance as the airplane travels. What's interesting about this is that, if you look at typically when we look at a map, we like maps on paper. Paper folds, it fits in your pocket, it goes on a computer screen, everything's flat, right? The surface of the Earth is not flat. So there's always something a little bit wrong and messed up about any map, any flat map. That's why they have globes, right? It's just they don't fold up and fit in your pocket very nicely. When you look at the most common map that you'll see out there is called the Mercator projection. And this is the one that's, it's kind of funny because, you have, North America, and then you have South America, and then you have, Greenland looks like it's this massive, huge thing up here. It's the size of the entire North America almost. Well, it's not. It's just that the map is really, really distorted up in the very northern and the very southern parts. Mm-hmm. And then you got your Europe over here, and Australia, and then there's Antarctica down there. That's a pretty good little map of the world there. It's not bad. So if you're going from New York to Moscow, it's tempting to say, oh, the shortest distance is a straight line, but
Yeah.
that's not this. This isn't the world. This is some highly distorted version of the world, and a straight line doesn't exist. A straight line would tunnel through.
Okay.
You know, you can't fly an airplane underground. And so it's tempting to say then, well, you just go in a straight line on the Mercator projection, but forget the Mercator projection's all sorts of weird, right? What you really want to do is fly along the great circle, and it'd be nice to know, what does that great circle look like on the Mercator projection? And what it looks like is it's kind of like this. It's bent upward like that.
That makes perfect sense.
Yeah, yeah.
When they say that if you're flying from New York
Yeah.
to London,
Yeah.
they always fly over.
Yeah.
They don't fly straight across.
That's what they don't fly what looks like straight across. That's right.
Straight across.
Yeah, that's right. Exactly. So this is why, and ultimately the reason why they fly in what looks like a curved path is because you're looking on a really weirdly distorted picture, and so it just kind of messes things up. And it looks like a complicated problem. Someone would observe, oh, the shortest distance isn't actually the straight line because of the Greenland phenomenon. Everything looks so big up here, even though it isn't. But things look a lot bigger than they are. Said differently, distances are actually shorter up here than they appear to be.
Okay.
And that's why they in some sense, go up here so they can take advantage of these actually shorter distances. And that's why what looks like a straight line is not the shortest path. This one is. Yeah. That's kind of a cool. Anyway, I think it's neat that while this looks like a very, very complicated problem on this picture,
On that picture.
on this picture you realize it's just angles and dot products. There's not that much to it.